sure that's all. Yep.
All right, so after each second, the velocity is going to change 9.8 meters per second. So at time 0, the velocity is 0, so this is time in seconds, the velocity in meters per second. After 1 second, 9.8. After 2 seconds, well, it's just twice. You keep adding this each time, so 19.6. After 3 seconds, 29.4, and so on. In essence, all you're doing is multiplying this number times 9.8. And so after 8 seconds, you could just keep adding 9.8 8 times, or just multiply. So the velocity would be that. So $88.6.
78.
Oh, yes, thank you. 78.6 units.
4, actually.
Any other mistakes? All right, so 78.4. I was only off by, it's like a misspelling, right? Units?
Meters per second.
There we go. And thank you for correcting me. Just cannot seem to get this tight. All right. How far does it fall? How would you figure that out? We've actually discussed 2 different ways of doing it.
Would you use like displacement to solve that?
Okay. How would you do that?
Is that a velocity times time?
Which velocity?
Average velocity?
Yeah, okay. So what's the average velocity?
Is it the 70.4 meters per second squared?
That's the final velocity, it's not the average. Unless I missed something that you said. It starts at 0, so that can't be the average of,
Okay, is that where you add them all up and you just like find the average of all of the velocities?
that's one way of doing it, yes. What's the faster way than adding them all up?
Divided by the total number.
Is it 14.7?
No, not 14.7.
14.1.
No.
8.7?
Is it 8.7? No. At the 14 point whatever, how'd you get that?
I added them all up and divided them by 1.
You added up the 5 numbers? And you divided by,
4 numbers and then I divided them by 5.
which 4, you added those 4 up?
The first and the last and divided by 8.
Yes.
That's what
All
I
you-
did.
If you're gonna add up all the numbers, please make sure you have all the numbers. I skipped from 3 to 8 seconds. So there's a 4, 5, 6, 7, and then 8. So, or you just average the first and last.
44.1.
No.
So we count 0 in there too?
Yes, 0 is part of the set.
39 plus
39.2. So there's the average velocity. So how far did it fall?
Is it 313.6 meters?
Maybe. How'd you get it?
Multiply 39.2 times 8.
Yeah, so unless you mistyped something. So you ended up with,
313.6.
so it fell 313.6 meters. What is another way of doing the exact same thing? And this is what was presented at the end of last class.
Is it the distance equals 1/2 gravity times time squared?
I think at this point I can nitpick that, not gravity,
Oh, acceleration.
the whole thing.
Wait,
You said the two major pieces to it.
distance equals 1/2 times acceleration times time squared. Is it average?
Okay, oh, okay. I'll go with that. In this particular case, what acceleration?
Average acceleration?
No, well, we're assuming it's constant, so,
A constant.
sure. Well, is it devolved into a read my mind exercise?
It's only when acceleration is the 9.8 meters per second squared.
What is 9.8 meters per second squared?
The acceleration during free fall. It's the gravity.
Say it again. I am nitpicking, but I know what you mean, and what, the spirit of what you're saying is
It's
right.
acceleration due to gravity.
There we go, that's the phrase I was looking for. Acceleration due to gravity. And what is the symbol used for acceleration due to gravity? Besides, we could use A. A is the generic term, generic for acceleration in general, but acceleration due to gravity, there is a specific letter that we use.
G? G?
What?
The letter G?
Oh, G?
Yeah.
Sorry to nitpick one more time. Uppercase or lowercase?
Lowercase.
Yes, all right. Lowercase g. All right, so the formula that you mentioned earlier, before I went on my tangent there, you did 1/2 at squared or 1/2 gt squared. Either one if acceleration is constant. This is specifically for free fall, and this is any generic acceleration, constant acceleration. Both assume initial velocity is 0. The initial velocity is 0. So, this is a formula for distance or displacement. Okay? So, 1/2 times 9.8 times 8 squared. And this should do a check to see if Rachel mistyped. .4 313.6. Either one works. This technique right here works regardless of what the initial velocity is. This technique over here works again with that assumption. All right, questions to hear? What is the distance that the object went? As Manal said that this was displacement, so I'm asking, what is the distance?
In this case, is the distance the same as the displacement?
There is a very subtle difference between the two, but yeah, if you were writing this on a test, if you wrote down 313.6 meters, yes, check. What is the subtle difference between the displacement and the distance?
Its direction.
Yes. So what assumption was made about direction?
Unidirectional. This problem is unidirectional.
It is unidirectional, okay, but there was another assumption that was made. As soon as I was told 9.8 meters per second squared, an assumption was made.
It's going straight down.
Almost there. What about down? How have we indicated direction anywhere in this problem?
Drop.
It did drop, but in our numbers here, I have 313.6 here, I have 9.8 there, 313.6.
8 seconds is positive, so you can assume that going down is positive.
There we go, that's the key. As soon as I was told this, there was a built-in assumption that down is positive. So, assumes down is positive. And therefore, a positive answer here means, well, they went down. Now, obviously, if I wrote the distance and the displacement here, they would look the same. From a nitpicking point of view, which apparently I do sometimes, you probably should state that down is positive if I ask for the displacement. Now, here I just said how far did it fall. That implies a distance there. And how fast is it traveling implies a speed. And so neither of these answers requires a direction to it. But we took it beyond what the original question was, because we are that good. Right. Any questions on this? Then, unless somebody comes up with a question, I'm not going to talk about chapter 3 for a bit, and we'll start on chapter 4. Actually, 4 and 5, I sort of blurred them together. 4 and 5 will go relatively quickly because a lot of 4 and 5 is about forces, and we've already talked about forces in chapter 2. Chapter 4 is when we combine chapter 2 and 3. I have a 5 kilogram box. I push on it with a 4 Newton force. This is the only force acting on it in terms of our F-town checklist. This would be classified as other, because I'm not specifying what's causing this 4 Newton force. Whatever's pushing on it with a 4 Newton force off to the right, there is some mystery object here where there's 4 Newtons pushing back in the other direction, but for this problem, we do not know or care about this. So the problem is I got a 4 Newton force pushing to the right on a 5 kilogram mass. And I'm just going to go ahead and say to the right is positive, just to make life simpler. So, if I have a 5 kilogram force sitting 5 kilogram mass sitting right there, and I push on it with 4 newtons of force, what is that mass going to do? Let's assume it starts at rest. Initial velocity is 0 meters per second. What will that mass do? Okay, yeah. Now, this is when the predictive aspect gets into it, because there is a relationship between chapters 2 and 3. The fact that the total force, and that stands for the total force, is equal to the mass of an object times its acceleration. So just plugging in here, we got 4 newtons is equal to 5 kilograms times acceleration. My 4 newtons is positive because, well, it's to the right, and to the right is positive. How do we solve for acceleration? Yep. My kilograms cancel out. My 5s cancel out. And so what is the acceleration of this object? All right, what's the math problem? Okay, so the math problem is 4 divided by 5. So 0.8, I guess you're a decimal fan instead of a fraction fan. That's okay. And units?
Newtons.
Are you stopping there?
Meters per second.
All right, I heard several different things.
Meters per kilogram?
Newtons per kilogram is one acceptable answer. And the other acceptable answer? All right, we'll put down newtons per kilogram. That, if you did that, it's correct. Now, how do you get newtons per kilogram? Well, it's because I have newtons over kilograms. What is another acceptable unit for the acceleration?
Meters per second squared.
Because in our formula here, if this formula is correct, the units must work. And so the SI unit for force, put a SI down there, the SI unit for force is the Newton. The SI unit for mass is the kilogram. The SI unit for acceleration is meter per second squared. And let me put the little SI. Have I done the square bracket thing to represent units yet? Is this the first time? Okay. So, SI units of whatever A is. I guess I should officially write it the same way. Or, if I just do it like that, that's just units of. Some textbooks, when they do this notation, they will do it slightly differently than what I just did. Some of them will sort of give it a little bit of flair there, and they'll do it this way. I don't, obviously. And what I mean by SI, what does SI stand for? If it had been originally done in English, it would have been IS, but it's French. However it's spelled in French. There might be an E over here. Standard International. No doubt my French accent was spot on. Which would be a refreshing change of pace to what it was in high school. International standard. And international standard, there were 7 basic units that upon which everything else is based. So meters, seconds, kilograms, and let's see if I can actually write kg as 2 separate letters. There we go. Kilograms are the 3 main ones that we deal with in here. From that, there are derived units. Newton is a derived unit. Which means that it can be expressed in terms of these. So a Newton, 1 Newton. The 3 lines here from like an equal sign, except I got a 3rd line. This means equal by definition. There's no great hidden secret to why what I'm about to write is true. It is true because the powers that be said this is what we're going to make it. So 1 Newton is equal to 1 kilogram meter per second squared, by definition. And just a little side note here, this equal by definition, sometimes you will see the equal sign with a triangle over it to mean the exact same thing. When I was doing more hardcore math, this is what I would see. Physics, this is what I see. So this is what I tend to use. I think OpenOffice equation editor. Oh yeah, OpenOffice equation editor uses that symbol. The other SI units, so let's see how well I can do this off memory. Let's see, there's also Kelvin for temperature. There is the candela for luminous intensity. The mole. How'd they get that abbreviation? Who knows? For amount, if you've had chemistry, this no doubt brings back some really fond memories. And the one I'm missing is I'll think of it in the middle of the night, wake up screaming. Obviously, those are the ones we deal with most. We do hit Kelvin at some point. We never deal with candelas in this class. It'll come to me later. Now, I did say that it was based upon seven units. The standards have changed within the past couple of years, and so they no longer define a meter, a second, and a kilogram as such. They define these other quantities from which you can derive these. But that other stuff we don't need to know for at the moment, or probably forever in the course. All right, back to the original problem. Any questions about anything on the board here before I erase? All right, so we're gonna go with a 6 kilogram mass here being pushed on by a 3 Newton force. It starts at rest. Assume the 3 Newton force stays constant. After 4 seconds, what is the displacement of the mass? What is the velocity? And so we are now combining multiple chapters. Since this part of the problem right here looks very much like what we just did in chapter 3, we can just set up a little chart here. Time in seconds and velocity in meters per second. We start out at 0. The problem lasts 4 seconds and starts at rest. So just from the chart point of view, the question is, well, how much does the velocity change each second? Well, what do you need to know in order to know how much the velocity changes per second? Yes, except I don't give it to you explicitly, but we have other information. I gave you a mass and a force from which you can find acceleration. Again, I know F equals ma. What is the force? What assumption did you just make? Yep. It is not stated in the problem. It was just stated by Manal, I believe. And that's equal to 6 kilograms. So it's positive 3 newtons, 6 kilograms times acceleration. So what is the acceleration? Pardon?
0.5.
Yep. Man, the mask in my hearing combination just not working. I thought you said 25, that's what.
I'm
that's
sorry.
No, it's not like I even listened to really loud music growing up to give me the tinnitus. It's just, I feel like I wasted it. Got it for nothing. All right, so I now know acceleration. So after 1 second, how fast is this object going? 2 seconds?
1.1.
All right, so it's going 2 meters per second, so we solved this one right here. This is 2 meters per second. Velocity, so we don't have to write the plus sign because we said up was positive, but let's just go ahead and emphasize the fact that it is in the positive direction. And the displacement.
Is it 2 meters?
How'd you get 2 meters?
Well, the final, well, I guess that's the velocity.
8 meters?
How'd you get 8?
2 meters per second times 4.
Except it's only going 2 meters per second at the end. Pardon?
78.4.
Whoa, no, how'd you get that?
Times 1/2 AC squared.
What'd you use for A?
9.8.
No, that's our acceleration here. All right, so you can do it that way right there. So we have 1/2 times 0.5 times 4 squared. So that gives us 4. So the displacement is in the positive direction, so positive 4 meters. Alternatively, we could have found the average velocity, which is 1 meter per second. So on average, 1 meter per second over 4 seconds, and just 4 times 1 is 4. Unless the math people have lied to us. Questions to hear before I change the problem?
Was there any other way you can find the displacement besides that formula?
Average velocity times time. So no one uses that formula. We've pretty much covered it. I mean, I can make it look different, but it's still the same technique. All right, let's change the problem. All I'm going to do is change the initial velocity to big. Negative 5 meters per second. We've established up as positive already, so we're going to stick with that. The velocity is negative 5 meters per second, which means it's heading down when the 3 newtons is pushing up. What is going to happen to this conceptually? This thing is moving down in the negative direction, but this force is pushing up on it.